Welcome back again to Surpac training. My name is Kobe and this is lesson number 12 of the Surpac tutorials, and in this lesson we will learn some basic variogram concepts. The image on your screen here outlines the topics that we are going to deal with in today's lesson. Someone may ask, what is the essence of getting to know a variogram as well as its parameters? Well, the reason is quite simple. From a variogram, you will be able to come up with something called the variogram map, which tends to explain the anisotropy of data and directional continuity. The parameters obtained from the variogram map will then be used in the various estimation methods. For example, you will need parameters such as maximum search radius, the bearing, the plunge, the dip, and the anisotropy ratios in most of the estimation methods, including inverse distance, nearest neighbor, and ordinary kriging. No need to worry if you don't understand whatever I have said. I will explain it to your understanding when we get to that stage. That was just the overview of what we are going to do in this lesson and the subsequent ones to come. So like I said, the image here outlines the topics that we are going to deal with. We will start with a variogram, then we will come to its parameters, nugget, cell, and range, and follow in that order. Now, before we move on, let's get ourselves familiar with some terms or terminologies, as these terms will be used one way or the other throughout this lesson. The first is a variogram. What is a variogram? I have some definitions here, so I'll pull the image of a variogram definition into graphics so we get to know what a variogram is. As far as geostatistics is concerned, a variogram is a graphical tool which provides a description of how data values change over distance and direction. In other words, it is used to characterize spatially correlated data. That is, it compares the difference between samples against distances. Okay, so that is the definition and explanation of a variogram. I'll bring an illustration of a variogram into graphics so we get to know how a variogram looks like. Whenever you create a variogram, this is how the shape should look like. Every variogram should take this shape. The image here explains theoretically how a variogram is created. First of all, you create an experimental variogram, in this case represented by the red points. Then afterwards, you fit a variogram model represented by the black curve here. Okay, so that's the underlying principle. You first create an experimental variogram from your population data, then you fit a variogram model to it. Okay. So aligned with a variogram are parameters called the nugget, the cell, and the range. I'll first explain what a nugget is. Nugget is the difference in value at a sample separation distance of 0. Okay, so if you want to understand what a nugget is practically, think of a sample, either a soil sample or a drill core sample, which has been splitted into two. Okay, then you take each half to different laboratories. Most of the times you will notice that the difference in the assay values that will be reported will represent the nugget. There will be difference in the values that will be reported for the assay values. So this difference represents the nugget. The difference in that halves of samples that were reported is what is referred to as the nugget. Very often, nugget is influenced by the type of deposit. So for instance, gold deposits have uneven distribution of metals, so they tend to have high nugget values, unlike deposits like iron that have even distribution and they are also very fine-grained. They have low nugget values. The cost of nugget is not only restricted to splitting of samples, but you can have factors such as human errors, analytical errors, and sampling errors. Sometimes when a sample is taken to the laboratory, there may be contamination of laboratory apparatus. So all these can lead to nugget. Now I'll bring back the image of a variogram so we take a critical look at how a nugget looks like. It's because of the nugget that a variogram doesn't start from the origin. As you can see, the variogram is always starting from the variance axis. Okay, whenever you split a sample into two and you take each half to different laboratories, if the values reported for each half are the same, that means that there is no difference between the assay values. In this case, the nugget is 0. That will make the variogram start from the origin. But such a condition is very rare in earth materials that we encounter. The earth material is anisotropic, it's not homogeneous, so you kind of cannot get samples when you split it into two. You can't get the same values for each half. Okay, there will be some kind of a difference, and this difference is what is referred to as the nugget. So the nugget will always make a variogram start from the variance axis. In this case, the nugget is sometimes referred to as the variability or the sample variability. That's why it's always starting from the difference or the variance axis. Okay, now I'll move on to the cell. So I'll bring the cell into graphics and we take a look at its definition. The cell is the variance value at which the variogram levels off. Practically, when you take samples in the field, when you collect samples in the field, you realize that the difference in sample values will continue to increase until at a certain point or distance, the difference between sample values becomes negligible. So that point at which the difference between sample values becomes negligible is referred to as the cell. So from the variogram graph, you notice that the cell is represented by the curved portion of the variogram. So from the nugget, you will notice that the difference between sample values will continue to increase until at some point or distance, the difference between sample values remains the same. And this is what is referred to as the cell. So sometimes the cell is referred to as the amplitude of the variogram. Okay. Now I move on to the range. So I'll bring the range into graphics and we take a look at its definition too. The range is the distance at which the cell is attained. Okay. So when I bring back the image again, you notice that it is the maximum distance. It's the maximum distance at which the cell is attained. Okay. Sample difference will continue to increase until at a certain distance the difference is negligible. The sample values, the difference between sample values will remain the same. The maximum distance at which sample values becomes the same is referred to as the range. So beyond the maximum distance, which is the range, samples are not correlated, as you can see from this image. Before the range, samples are correlated. That is, the difference between samples will continue to increase. But beyond the range, that is the maximum distance at which the cell is obtained, samples are not correlated. That is, autocorrelation is 0. Okay, so now that we are through with nugget, cell, and range, let me take this time to explain the difference between these terms. Okay, we have here isotropy, anisotropy, omnidirectional variogram, and directional variogram. So I'll bring the definitions of these terms into graphics, starting with isotropy. Isotropy refers to a condition in which values measured in different directions are the same. Okay, that is, the material will have the same value when measured in different directions, and such a condition is referred to as isotropic. So it's as simple as that. Then I go to anisotropy. For anisotropy, the name speaks for itself. It has different values when measured in different directions, and the condition is referred to as anisotropic. Okay, so take note the difference between isotropy and anisotropy. Then I come to omnidirectional variogram. Omnidirectional variogram is the type in which sample pairs are selected based on separation distance and not on direction or orientation. So the term omnidirectional means it has no direction. The variogram is based, the sample pairs are selected based on the separation distance. Okay. Then we move on to directional variogram, which is the last one. In this type of variogram, sample pairs are selected based on a particular direction or orientation or azimuth. Okay. So note the difference between directional variogram and omnidirectional. The omnidirectional has no direction. Sample pairs to be used for variogram calculation are based on separation distance only, whereas directional variogram sample pairs are selected based on a particular azimuth or orientation. Okay, so now that we understand all the terms, let's move to the task at hand, which is creating a variogram, which is the tool to explain how data values change over distance and direction. Let me close my definition folder so that my work directory becomes simple. Okay, now we move to the task of creating a variogram. I'll head over to database analysis, then select variogram modeling window. Okay, another way of opening this variogram window is to go to block model, geostatistics, then you come to variogram modeling. It's the same window. Now when you come here, the first thing that you want to do is create a variogram for your string file. The string file is the composite file, which is free of outliers. Remember, in the previous lesson we dealt with the outliers we had in our data set. So quickly you head over to file, new, string file variogram. Okay, we are performing a variogram for the string file, that is the composite string file. Okay, and the variogram calculation window will appear. Another way of opening this window is to click the first icon here, which says load data from a string file. I'll select it. Okay, so as you can see on this window, we have two tabs. We have basic and advanced. I'll explain whatever parameter that is indicated on this form. I'll begin with the basic. Location. This is where you select the string file or the composite file, which is free of outliers. The ID range, if a number is attached to the file, it will appear as the ID range. If you want to constrain your string, then you enter the string numbers here. Then we have D field. This is the same as description field. As you can see, D1 has been selected as the default, meaning the first description field. Don't forget, the first description field of your composite contains the gold values, and you have cleared it off outliers. Okay, so that has been selected as default. And we have here minimum value and maximum value. These are the minimum constraints and the maximum constraint values respectively. When you enter a value here for the minimum value, samples with values less than the value that will be entered here will be discarded or ignored. For the maximum value, samples with values that are greater than the value that will be specified here will also be neglected, okay, or discarded. So this is kind of constraining your gold values or description values. Then I come to data selection windows. As part of higher versions of Surpac, that is Surpac that is created by Jovia Surpac version 6.6 upwards, you get the options to select the type of data selection window. For a two-dimensional or a 2D case study, the search for sample pairs, that is when you are searching for samples, the search for sample pairs takes the shape of a pyramid. Okay, so you will see in higher versions of Surpac, you will see an option to select a pyramid or a cone. For 3D case study, that is in our case, the search for sample pairs will also take the shape of a cone. Okay, so you will see two data selection windows, either a pyramid or a cone. For a cone, that is related to 3D, and the pyramid is related to 2-dimensional. Okay, now as you can see, we have some new terminologies here, or new terms: azimuth, plunge, spread, and spread limit. Let me spend some little time to explain the meaning of all these terms you are seeing here. Okay, so I'll close this window, I'll come back to it. I'll go to my navigator and I'll open this image here to explain to you the meaning of those terms. Okay, so this image here practically explains how samples are collected in the field. Okay, this is the north, that is the y-axis, and this is the x-axis. The black line here refers to the direction along which sample pairs are collected, or the azimuth. So let's go straight to the definition of azimuth. The azimuth is the bearing of the axis of the cone or cylinder and has values between 0 and 360. And of course, azimuth or compass directions have values between 0 and 360. It's the same with this diagram here. The blue line here is the azimuth, or the direction, or the bearing. Okay, as you can see, bearing is always measured with respect to the North Pole. So the direction is from the North axis here. That's why it has been indicated direction blue here. Okay. Now, the lag here, okay, the lag refers to the sample spacing. That is within each sample spacing, the samples that were collected, as indicated by these points that have been circled with red, okay. So within this lag, these were the samples that were captured. So the lag refers to the sample spacing, okay, as indicated here. Then the plunge is the angular displacement of the axis of the cone or cylinder from the horizontal axis and has values between -90 and 90. So the plunge is some kind of the dip, okay, the dip of your search or the dip of your axis of the search window, okay. Then I come to the spread, okay. Along this search from one sample point to the other along the particular direction or orientation, you realize that when you are searching for samples, it is within a certain tolerance angle. This tolerance angle is what is referred to as a spread. So the definition of a spread can be seen here as the angular displacement of the edge of the cone from its axis and has values in the range of 0 and 90. Okay, so it's the angular displacement of the edge of the cone. So the angular displacement from the axis refers to the azimuth or the direction. As indicated here, this red line here is shown as the tolerance. So the angular displacement from the azimuth here is what is referred to as the spread. So another name for the spread is the tolerance, as indicated here. Okay, now the very moment you specified an angle to limit the spread, okay, such that you don't go beyond your spread angle, then the search window becomes a cylinder, okay. So as indicated by this green here as the bandwidth is the same as the spread limit, okay, as indicated here is the same as the spread limit. If you take a look at the definition of the spread limit, it says it is the offset of the edge of the cone from its axis where the search window will become a cylinder, okay, the offset of the edge of the cone. So at a certain distance from the edge of this cone, okay, the search window becomes a cylinder as indicated here. So the spread limit is the offset from the edge of the cone. That makes the search window a cylinder, and the spread is the angular displacement from the search line or the azimuth as indicated here. Okay, so I'm pretty sure we understand the definitions of the azimuth, the spread limit, plunge, and lag. Okay, so we'll go back to our window. I'll go back to File, New, String File Variogram, and the window will appear. Okay, then I come to lag. We have dealt with them. Then I come to lag. The lag is the sample separation, like I just said. Okay, so along the drill holes, at which distances were samples collected, you enter that value there. And the maximum distance, sample pairs greater than the value that will be entered here will be ignored from the variogram calculation. Okay, so if a distance of 50 is specified here, then beyond 50, samples at distances of 51, 52, and so on and so forth will not be included in the variogram calculation. The output file name, you can enter a name for the report that will be generated for the variogram calculation, and you can choose any format to save your report. Okay, you can choose to check this box if you want to display the report. All right, then I'm done with the basic tab. I'll go to the advanced. We have geographical constraints, minimum and maximum. These fields here, you enter values to constrain your data geographically. We came across this field when we were dealing with how to create a histogram. Okay, the values entered here are used to constrain your data geographically. So minimum y, x, and y, z coordinates, you enter them here so that values that are less than the coordinates will not be included. Likewise, the maximum values for x, y, and z coordinates, the values greater than these values will not be included in the variogram calculation. Good. Now I come to the lag slider. We have minimum, maximum, and the increment. This is the lag slider. Okay, it is the tool used to modify the lag. Okay, so you specify the minimum value. It's like a meter rule. Okay, you specify the minimum value and the maximum value, as well as the increments, the distances that you want to move. Okay, then I come to treat negatives as. When you select zeros, negative samples will be assigned a value of 0. When you select undefined, negative samples will be discarded or will not be included. When you select negative, negative samples will be retained. Okay, they will be maintained as they are. You can also check this box to create a cross variography for your data if you want. Okay, so now that we understand what is indicated on the basic and advanced tab, let's go ahead and fill it up. Location, I will go into my work directory, then I will choose my composite file. Okay, so I'll go into my work directory, then I'll select composite top cut. Notice that there is 2 attached here, and these 2 will go to the ID range field. Okay, so I'll select composite top cut, open. You see the 2 has appeared here. Okay, then the D field, I will leave it because the description field 1 contains the gold values. I will not apply any constraint to it. Then the azimuth. Okay, here the focus is with respect to the omnidirectional variogram. Remember, omnidirectional variogram is the type that in which sample pairs are based on separation distance only and not on direction. So if it has no direction, it means azimuth is 0. Okay, plunge 0, and the spread is 90. So these are the conditions for omnidirectional. It is with respect to the omnidirectional that we will be able to determine or calculate our nugget. Okay, if it is omnidirectional, that means the azimuth is 0 and it has no particular direction, and the focus will be at a specific point. So if it's at a specific point, then it means that the nugget is of interest to us. What is the difference between sample values of a particular point taken at a specific point? Okay, so these are the conditions. For omnidirectional, azimuth is 0, spread is 90. We can create for other orientations. I'll right click and select add. Then I will enter here an azimuth of 0, a plunge of 0, and a spread of 45 degrees. Okay, so you notice that the higher the spread, the more samples that are captured. I can create for another azimuth or orientation, let's say 45 degrees, a plunge of 0, and a spread of 22.5. Okay, so if you look at these 3 parameters that we have specified here, these 3 rows, the first one refers to an omnidirectional condition where the spread is 90, azimuth is 0. The second one here is not omnidirectional, even though the azimuth is 0. The spread is 45, and this is what is not making it omnidirectional. Okay, the 90 is what makes it omnidirectional. Then we have here directional variogram because we have specified the azimuth to be 45 and the spread is 22.5. So a spread of 45 will capture more samples than 22.5. Then I come to the lag. In my database, samples were collected at intervals of 1.5 downhole. Okay, so I'll enter 1.5 here. Then the maximum distance, I'll specify, I'll leave it as 50. Output file name, I will enter experimental variogram because we will first create an experimental variogram and fit a variogram model to it. I want the format to be a note file. I will display report. Okay, let's display the report. Then I go to the advanced section. I want to apply any constraint to my data geographically, so I will leave the minimum and maximum coordinates fields blank. Then I come to the lag slider. So the minimum value, I would want to enter 1. Then the maximum value 50 at increment of, let's say, 0.5. Okay, so this is something like the meter rule. Okay, that is used to the graphical to use to adjust the lag. Then I will treat negative samples as they are. I won't create any cross variogram for my data. Okay, so now we have filled the form. Let's see what comes up. I'll click apply. Okay, and it will start processing the samples. So in no time, the experimental variogram will be displayed. It will take some time. Okay, so like I said, the underlying principle is creating an experimental variogram from your population data. Then afterwards, you fit a variogram model to it. So when it comes, you will see that the experimental variogram is kind of a scattered diagram which has been joined by several lines, okay, to create something like a curve. Okay, so this is the report you are seeing here, variogram calculation. This is the composite top cut 2 file. The string, we perform the variogram calculation on all the strings. This is the name of the report. The description field is D1. All ranges, the lag is 1.5, the maximum distance is 50, the parameters we specified. Okay, so for an azimuth of 0, plunge of 0, and a spread angle of 90, this is the omnidirectional condition. Okay, these were the statistics that Surpac gathered for us. Okay, then you come to the azimuth of 0, plunge of 0, and a spread angle of 45. These are its statistics. Then you go to the third condition, an azimuth, the directional variogram, an azimuth of 45, plunge of 0, spread angle of 25. These are the statistics. Okay, so you have the drift, the gamma. The gamma is the same as the variance. We have the weighted gamma, the logarithmic gamma or variance. We have the general relative, the pairwise relative, and the average distances. Okay, so this is the report. It will go into my work directory. So as you can see, we have here the experimental variogram. Okay, this is created from the population data. Okay, so this is what we will fit our variogram model to. Okay, and this is the lag slider. Remember, the minimum value was 1 and the maximum value here, if I drag this here, the maximum value will be 50 at intervals of 0.5. So when I click this, it moves to 1.5, 2, and so on and so forth. Okay, but 1.5 is indicated here as default because we specified the lag to be 1.5. Good. So this is the vertical as is the gamma. This is the same as the variance, okay, or the difference. And this is the distance or the lag. And this is the legend. The normal curve here refers to the experimental variogram, and the green line here is the variance of your data. Okay, as you can see, we have these 3 tabs here. Okay, these were the parameters we specified for the data selection window. The first value here refers to the plunge. The second value here refers to the azimuth, and the one in bracket refers to the spread. So for the omnidirectional, the plunge was 0, the azimuth was 0, and the spread was 90. And the second condition, we specified a plunge of 0, an azimuth of 0, and a spread of 45 degrees. Then the third one, which is a directional variogram, the plunge was 0, the azimuth was 45, and the spread was 22.5. Okay, all right. So as you can see, this is the second one. You can see this one has more sample pairs than the 22.5. Okay, so the higher the spread angle, the more samples you are likely to capture. Okay, all right. So except for omnidirectional condition where the spread is 90, you should choose a moderate angle for your spread. Okay, so now that we have our variogram created, let's look at some of the things that we can do. The first is we are going to create orientations. As you can see, these are the orientations. We have this an orientation or azimuth or direction of 0. We have here an orientation of 0, and we have here an orientation of 45. Okay, so we will go to display, then you select all orientation charts. This will create a chart on which all these orientations, the 0, 0, 45 will be indicated. Okay, so it's a chart for all the orientations. So I'll click on that, and you see an all orientation tab has been added to the 3 orientations. Let's see how it looks like. You see, this has displayed the omnidirectional variogram, the second variogram, and the third is the directional variogram. Okay, and it's indicated by the legend here. So the black here refers to the omnidirectional, the red one refers to the second tab, and the third one, which is the blue, refers to the directional variogram. Okay. Again, you can right click on, you select any of these tabs, then you right click and you select tile windows. This will kind of create rectangular images for all the variograms. Okay, so this is how it looks like. The very moment you click on a tile, it becomes highlighted in red. Okay, so now the 090 is what I right clicked on, that's why it has been highlighted in red. When I click on this, it will be highlighted in red. Okay, then I come here, I click on it, it's highlighted red, and this is the all orientation chart. You can right click on any of these and go back by selecting tab windows, and you get back to your window. Okay, now another thing that you can do is to also save your experimental variogram so that you can call it for future use. Okay, you go to file, save, then you select experimental variogram. So we will say experimental variogram. Apply, and it will go into my work directory. So in the message window, when the file is saved, it will appear experimental variogram.evg. The EVG is the file extension for experimental variogram. Okay, so now let's look at some of the things that we can do after we have created our experimental variogram. Go to display, then select display or hide number of pairs. Okay, this will show the number of pairs that were captured for each lag. Okay, remember these are the lags or the distances. Okay, you can go back. All the functions indicated here are shown here. Okay, you can use, it's the same icon here. You can choose to send them away. Okay, you can go to display, hide, or display variance, and the green line will disappear. It's no more showing in the legend. Okay, I can bring it back by clicking on this icon. It's the same thing. You can go back to display and select Kriging weight. We have not created a variogram model, so you cannot display the Kriging weight. Okay, we have already dealt with orientation chart. Then you can select a marker position. You can choose to display evenly spaced for your markers, or you can use weighted spacing. Okay, whatever you want, you can choose to select that. Then I go to display again, then set axis limits. Click on that. This shows you can adjust the limits, okay, the maximum values for your axis here. The maximum lag distance is 49.5 because this point here is on the 49.5 mark. It's not up to 50. Then the maximum gamma is 0.6 as indicated by this point. And the minimum gamma or variance value is 0. That is the origin here. Okay, so you can choose to enter a maximum value, let's say 50 here, and you have that value set for you. Okay, then I go to display again, then click on display or hide grid, and the lines will disappear. Okay, you can bring them back by clicking on this icon. You can use this icon to also display your axis limit. Okay, you can go back to display again, then you can choose to hide the legend that was shown here. Okay, you can bring it back by clicking on this icon, display or hide chart legend. Beautiful. Then I go back to display again. Then you can choose to hide or display the lag intervals. Okay, so these rectangular things you are seeing here represent the lag. Okay, so for this lag, these are the number of pairs that were captured. Okay, 291. Within this lag or distance, the number of pairs was 271, sorry. Then this one you have 253. Okay, so these are the lag intervals. I can take them off by clicking on this icon. Okay, now another thing that we have to take note is the types of experimental variograms that we have. Okay, the types of experimental variograms that we can have. You go to variogram, then you select type. Okay, The same icon is indicated here. When you go to variogram type, the same icon is indicated here. Okay, we have several types of experimental variogram. The default one is the standard. Okay, as soon as you create your experimental variogram, the one that is displayed, okay, as indicated from the right side here, is the standard experimental variogram, and the variogram model is spherical. We will come to this. Okay, the cell value will be indicated here, the range will be indicated here, and the nugget value will be indicated here. Good. So you can click on this icon, or you can go to variogram and select type. Okay, so here we are to note the different types of experimental variogram. Let me click the drop down. We have normalized, logarithmic. These were what were displayed in the report for the experimental variogram that we opened. Okay, the logarithmic, the general relative, and the pairwise relative. You will notice that when I select any of these, it changes the gamma values. Okay, that was why you saw log of the variance, the PW, which is the pairwise relative of the variance, and so on and so forth. So notice it when I click on any of these. Normalized, apply. You see the values have changed over here. I can go back and select logarithmic. Okay, and the values will change. I can go back and select general relative, apply, and the values will also change again. So all the types of experimental variograms changes the gamma or the variance values or the vertical axis values. Okay, pairwise relative, apply. You see the values have changed. I go back and I'll select the standard one, which will take me to the default, apply. Okay, beautiful. Now we move on to the main task, which is creating a variogram model. As I said initially, the underlying principle is creating an experimental variogram and fitting it with a variogram model. So let's get to that. Let me display my variance. Okay, so the green line has appeared as indicated from the legend. Okay, without an experimental variogram, you cannot create a variogram model. And when you after creating a variogram model, and you want to display it, you first have to load your experimental variogram before you superimpose your variogram model. Okay, so now quickly let's create the variogram model. I can go to variogram menu, then I will select model. Okay, the same icon is indicated here, model variogram. If you don't want that, you can use the variogram menu, then select model. I'll click on it, and a variogram model will appear, which is the best fit for my experimental variogram. Okay, but you can adjust this to suit your preference. The very moment I brought the variogram model, notice that the parameters have been filled here. The cell value is 0.387, the range is 5.153, and this is the nugget value. Please don't be confused with the positions of the nugget and the cell. Okay, the structure 1 is referring to the first variogram. We can create additional structures. We will get to that pretty shortly. Okay, so the nugget is the first value, followed by the cell and the range. So for this structure, the cell is 0.38 and this is the range value, and the nugget is 0.086. Okay, so now we can adjust the nugget to suit our curve. Okay, you can adjust the lag slider values to get a better experimental variogram, but this is not all that necessary. Let's see how it looks like. When you continue to increase the lag or the spacing, the lag spacing, you notice that your experimental variogram becomes more smooth. Okay, so let me get back to my 1.5. Okay, now it is required that you fit your variogram model to the first 3 or more points or first 2 or more points. Okay, so I can drag my nugget value. These blue dots are what is used to adjust the variogram model as indicated here. You see now we have some new terms added to the legend. We have the variogram model and the variogram structures. The blue here refers to the variogram structures, which is used to adjust the variogram, and the red is the variogram model. the black is the experimental variogram, the green is the variance. Perfect. So I can drag this here to fit my variogram. Okay, passing through the first 3 points to suit what I want. Okay, if you want to add another structure, you can go to Variogram, then you select Add Structure. The same icon is indicated here. When I click on Add Structure, it will bring additional blue dots so that I'll be able to adjust the Variogram in such a way that it will fit more points. Okay, so notice it when I click on this icon, Add a Structure, or Variogram, Add a Structure. You see another blue has appeared here, so I can click this one and drag it, okay, to help me adjust my variogram. Okay, this is not all that necessary, so I can delete this. I can go back to variogram and select delete structure. You see the minus sign is here. I can use this icon here and it will delete this blue structure for me. I'll click on that and you see the blue dot has disappeared. Okay, when you add another structure, it fills up the values for the parameters for that structure. You see structure 2, we have the cell values and the range values here, and the nugget remains the same. Okay, this is the nugget value. I have not touched it. Okay, so when I delete it, the values for the structure 2 will go away. Okay, you see the values have disappeared. Okay, so now we have my I have set my nugget to be 0.0537, and this is I have my cell and range values. I have explained all these terms. Okay, so I will just try and fit the model to the first 3 or more points. In doing this, you can ignore sample pairs that have low values. Okay, all right. We are putting the variogram model on the omnidirectional variogram. Okay, we didn't fit it to any of these because the omnidirectional is what will help us obtain the nugget. Notice that, okay, because omnidirectional variogram has no direction. Okay, that is why we are fitting the variogram model to the omnidirectional one. Okay, and we didn't fit it to any of these. Okay, so we now have our nugget values. Let's look at some of the things you can do after creating your variogram model. There are several types of variogram model. I'm sure most of you out there know that. You can click here. You see we have spherical model, which is the commonly encountered variogram shape. Okay, you see this is the variogram model. The default is a spherical, so whatever model we have displayed here, variogram model is the spherical type, so it's the most common types of variogram model. Let's select exponential and see. Okay, you see the shape has changed. The exponential is similar to the spherical, but it rises more steeply and reaches the cell asymptotically. You see that it doesn't get to the actual cell value, it continues to rise exponentially. And the very moment you change the variogram model, it is indicated here. Okay, the same icons are indicated here: the variogram model, delete variogram, add structure, delete structure, and the variogram model is you can choose the Gaussian too. Okay, the same thing is here: variogram model type Gaussian. Okay, the Gaussian implies short scale continuity and it has a parabolic behavior. You see, it's kind of curved at the origin here, so it has a parabolic behavior at the origin instead of a linear one. Okay, you click on this and you select the whole effect. Okay, and you see that the whole effect has a sinusoidal kind of shape or a wavy kind of shape. Okay, so let me go back to when you select the variogram model, you see the shape change on this icon here and it's indicated here. You can go back, variogram model type, and select the default one. Okay, if you have made any wrong modifications on your variogram, you can go back to variogram and select delete model and it will disappear. Okay, you can bring it back by creating a new model. Okay, all right, so now the last thing that we are going to do is to save a copy or we create a report for the variogram model. we have saved the experimental variogram, and now we can save the variogram model. Go to File, Save Variogram Model. So we will save this as variogram model, so that in future we can call it and do whatever analysis we want. I'll click Apply, and you see in the message window, variogram model.vgm has been created. The VGM is the file extension for variogram model, and the EVG is for the experimental variogram. Okay, so now we have saved the experimental variogram and the variogram model. I'll go ahead and create a report so that it will save these values, the nugget, the cell, and the range. I can click this icon here which says variogram report, or I can go to variogram and then select report here. It's the same thing. Okay, again, you can use this icon here to select variogram report. There are several ways of killing the cat. And the very moment I click on that icon, variogram report, you see that the model type is indicated here as spherical. The nugget value is indicated here 0.0537, the same thing here. And the number of structures, remember we have only one structure, so it has been indicated here. The cell and the range values are indicated here. If we had more than one structure, the rest of the values will fill up here. And you can give a name for your report. Let's say nugget value, or simply nugget. Okay, so we can call this anytime that we want. Remember, the nugget value should be used out throughout your variogram analysis. Okay, so I'll click Apply, and the nugget will go into my work directory. We can take a look at it. So I'll go into my work directory, and then I can minimize this window, and I'll come back and refresh this. Okay, you see this is the nugget. I'll open it. So this is the report for the nugget. It's a spherical model. This is the nugget value, the cell, and the range. We only have one structure. Okay, so that is it for variogram studies in this lesson. In the next lesson, we will learn variogram map, and that will help us to get anisotropy ratios, and we'll take it from there. Thanks for watching, and please stay tuned for more tutorials, and don't forget to subscribe or comment. Thank you, and catch you later in the subsequent lessons. Bye for now.